As I'm sure you're all very well aware, Project Phase 2 is going to be due this Friday. And very shortly thereafter, or in fact, actually, hopefully, maybe even by Thursday or so, we'll be posting Phase 3 so that people can start going on that. You'll have some more time for Phase 3. I believe it's about 2.5 weeks. That'll take us all the way until essentially Monday, kind of right before the final. And I believe that's May 7th or something like that, but I'll have to double check the exact date. So you certainly have some more time for that third and final phase of the project. But as I've mentioned a few times already, it does have a lot more complexity in it. You'll really be able to kind of play with the entire link, transmitter, amplifier, comparators, etc. And so definitely this is something you're going to want to make sure you start well in advance on, because it will take you some time to just understand all the different trade-offs in the pieces and figure out really how you'd optimize the design. So with that, any questions on either material or project or anything like that? How many of you guys have started Phase 2? Okay, great. I guess the high success rate here is why you guys are actually in class as opposed to not here at the moment. But hopefully the people who are not here at the moment are also hard at work on the project. So if there's no other questions, let's go ahead and dive back into the material that we had left off with last time. And I believe where we basically ended up was talking about how we would now finally actually implement some of these regenerative comparator types of structures. So if you remember, I believe we had ended last time on basically saying that you really want to use these so-called regenerative or cross-couple types of devices, largely because this really would save you quite a bit in terms of the bias current you'd have to spend in order to get a certain amount of regenerative gain. And so where we basically ended up was with this so-called CML comparator, which is also known, by the way, as a CML latch. As I believe I mentioned last time, CML just stands for current mode logic, which is kind of the logic style that was actually quite popular for some time when people were using bipolar junction transistors. Because it turns out with BJTs, you obviously need to be running current through them pretty much constantly in order to get things to work in a reasonable way. So this particular sort of design here was actually used even for digital latches. In our particular context, obviously, we're really trying to use this as a comparator. And as we had talked about last time, and just maybe to refresh, the way this design works is that when the clock is low, then in some sense the whole thing is hooked up to look essentially like an amplifier. Right? So we've got the bias current flowing through this input pair here. These cross-coupled devices essentially are shut off. And so the whole thing essentially just looks like a resistively loaded amplifier. However, once the clock goes high, we essentially turn off this input pair and turn on these cross-coupled NMOS devices here. So the whole idea being that essentially as long as the GM of these is large compared to the load resistance, so that on the net you see a negative resistance or negative impedance looking into that node there, then essentially you'll exponentially regenerate whatever initial input was sampled right when the clock basically went high. Okay? Yes? Okay, so the question was, why is it that this cross-coupled kind of thing provides a negative impedance? And so remember, and let's even just call it negative resistance. So remember, resistance is just the slope of the I versus V curve. Okay? So if you think about this kind of structure, and particularly you have to think about it from a differential impedance standpoint. So basically, if I was to move the voltage up, for example, on that side, okay? That would then imply that, of course, there'll be less current flowing on this side, right? Which would then cause actually even more current to flow in that direction. So in other words, what's happening is that when you move the, like in other words, let's say, I'll be careful actually now. Oops. Okay, so if this voltage goes down, right, that means that less current is being pulled down from this transistor. Okay? So in other words, what we've just said is that if I do a plot of I versus V, if I increase V, the current actually goes down. So that's exactly a negative resistance, right? Because if it was a positive resistance, the slope should have gone like this. But as we just said, I increase the voltage, current actually goes down. Okay, that's why it's essentially acting like a negative resistance. Exactly. So I increased the voltage in the left branch, and then the current in the left branch also went down. Okay? That's exactly why it's acting like a negative resistance. And by the way, you can do a simple, like, apply a differential current source or differential voltage source, measure the opposite parameter. You'll see, indeed, it ends up being negative, at least from a small signal standpoint. Okay? Okay, so it's useful to sort of think about this as I mentioned before, when the clock is low, this is really sort of acting like an amplifier. And when the clock is high, that's really when you do the regeneration. Now, I want to explicitly sort of call out these two different phases, because as we'll see in 1 second, there's other types of structures that will look initially a lot more complicated and will sort of behave in a somewhat funny way, but will also essentially be, you can classify their operation into exactly these two kinds of phases as well. Okay? In fact, there may be an additional phase we'll introduce, but nonetheless, you can still think of things as initially amplifying and then regenerating. Now, as we had mentioned last time, this structure is actually quite straightforward to kind of think about and analyze. And so when we get to phase 3 of the project, this is exactly the type of comparator that I'll give you. But it does have some disadvantages associated with it. And the principal disadvantage is that usually at the end of the day, you want your digital signals coming out to have sort of full VDD to 0 swings coming out of them. Whereas in this particular design, as we talked about last time, your swings are really just set by essentially I bias times R. Okay, so the maximum sort of, once you've regenerated, you only end up with a signal that's either at VDD or VDD minus I bias times R, which obviously is not, in general, going to be the full power supply range. So what I'd like to do now is draw another type of comparator, which interestingly enough was actually invented for digital applications, but I believe has actually found the by far greatest use in the sort of analog mixed signal types of designs, which is called the strong arm latch, or the strong arm comparator. And again, the big difference here is going to be that this design will actually give us a full 0 to VDD swing at its output. Now, as you can probably imagine, almost all of these comparator types of structures end up having some kind of cross-coupled, let's say, inverter-looking kind of thing inside of them. So let me start out by kind of drawing that, and I'll do it at the detailed transistor level, and you'll see why in 1 second. So if I was to start out with sort of a cross-coupled inverter, and this picture may initially look kind of funny, but believe me, this is basically just an inverter. Okay, so indeed at the core of this thing is going to be this kind of cross-coupled inverter. But rather than tie the sort of sources of the NMOS transistors to ground, what I'm instead going to do is actually couple them to something that essentially looks like a differential pair input. Okay? Now, in particular, as I mentioned before, this thing is going to have to be in some way clocked. Because as we saw even in our original picture of these cross-couple things, if we didn't have some clock somewhere, there wasn't really any way of knowing kind of, do you want to be grabbing the input, or do you actually want to be doing regeneration, or doing something else? Okay? So I'm going to put a clock input down there. This is, for example, going to be, let's say, VI plus, VI minus. Now, to actually really make this thing work, there's a couple of extra transistors I have to add here, which I'll explain what they're doing in 1 second. Okay, so it turns out I'm actually going to add sort of these clock transistors here as well. And our differential amp outputs are going to be taken like this. So this would be, for example, VO minus. This would be VO plus. Okay? Now, the reason why I needed to add these things up over here is that notice when this clock is when this clock is off, meaning the clock is low, this transistor is just totally turned off. Okay? So that would mean that there's kind of no pull-down path associated with these things. And as we'll see in 1 second, what I really need to do is essentially get this thing to some initially predefined state in order for it to actually operate the way we intended it to. So these extra clock transistors I added up over here, they're really just pre-charge devices, just like you probably heard about in 141 with dynamic logic. So initially, both of these outputs are going to start at VDD. So let's think a little bit about what would happen essentially to these waveforms at the output versus time. So this is just going to be some voltage versus time, and let's actually just say it's VO plus and VO minus. Okay? So let's say that the clock actually goes high right at this time right here. So as we mentioned a second ago, because of those pre-charged devices, when the clock is low, both of those outputs should just start at VDD. The whole thing is just a pre-charge gate, nothing really strange happening there. All right, so now you guys tell me, once the clock goes high, what's going to start happening to those outputs? And by the way, of course, when the clock goes high, these pre-charged devices turn off, and this tail device down here turns on. So what's going to start happening to those outputs? Yeah, they have to start discharging. There's kind of no other direction they can move. Now, the key thing to realize is it's not just that they discharge, but actually they'll discharge, if I look at the differential output, they'll discharge at slightly different rates. Because notice, if I put a differential input into the structure, then the amount of current I have flowing on one side versus on the other side would be different. So again, let's just sort of sketch that. That would mean both of these would start going down, but one of them would go down faster than the other one does. Okay? Now, at some point what's going to happen is that when you get down far enough, and let me just, let's pretend that that's down, let's say, to somewhere like here, then what will actually happen is that this cross-couple inverter will start working the way it's supposed to. In other words, it'll start actually acting like a regenerative amplifier. And so at that point, whichever side is lower should actually exponentially basically get even lower, and whichever side is higher should exponentially essentially become larger. And then at that point, obviously, once you sort of hit the power supply rails, you've basically made your decision. Now, in case it wasn't obvious, the point at which this really starts happening, roughly speaking, is associated with a threshold voltage of these PMOS devices. Right? Because you have to get these two nodes low enough in order for the PMOS to actually start turning on and pulling the output back to the high voltage. So this kind of discharge and then regenerate behavior, in fact, is actually intentional. So just to make sure it's sort of clear, I again wanted to kind of classify this a little bit as we had mentioned before. You can really think of this as essentially acting as an amplifier in this first phase, where both of them are discharging down. And in this second phase, that's really when it's being regenerated. Now notice that unlike in the previous example with a CML latch, here it's not really the clock that tells you whether or not you're amplifying or regenerating. It's actually sort of an analog voltage in the circuit that, once you cross a quote-unquote threshold, that's really how you decide whether or not you're quote-unquote amplifying or quote-unquote regenerating. So this circuit actually turns out to be a very, very popular way of building these comparators. But it does have some, let's say, funkiness associated with it. Okay? Because as we said a second ago, there's kind of these multiple different phases of operation. Initially, you do this discharge and, let's say, sort of quote-unquote amplify, and only then do you start doing this regeneration type of operation. And in fact, I've oversimplified it even a little bit too much here in that, obviously, when these things turn on, first you have to discharge these internal nodes before you can actually even do anything at the output. So there's even yet another sort of, let's say, phase of operation here. But the good news is that especially if you sort of think about it a little bit carefully, you can get a pretty reasonably good model for essentially what the behavior of the circuit is, and therefore what all of the characteristics you might care about really are. So things like input-referred noise, let's say the input-referred quote-unquote gain during the amplification phase, and so on and so forth. Now, I don't want to spend too much time on that here right now because, again, there are a lot of details there that, especially when the first time you look at them, may not make a lot of sense. But if people are interested, please feel free to come and bug me. And in fact, if you're really, really interested, for example, in how you'd evaluate the noise of this kind of structure, which is even more, let's say, funky just because of the time-varying operation of the circuit, it turns out Pierluigi actually wrote a paper about this back before he even came to Berkeley. So he'd be another great person to kind of go and bug about how you might think about the noise of this type of circuit. But for now, it's what I'm sort of most interested in is making sure that people understand the general idea of how this kind of structure would operate. So any questions on this? Or? Okay, so again, I would actually encourage you to try and do, let's say, a simple zero-order analysis as to, for example, how much gain you might get during this initial amplification phase, in terms of, or rather, by the time you actually start regenerating, how big are these differential signals relative to the inputs. Turns out, again, that's not too difficult thing to do. And if you manage to understand that, it gives you a really good insight in how this particular structure is working. Now, having said that, I now want to move on to talk about some of the additional characteristics we said were really going to matter in these comparators. And I wanted to do it in the context of this strong arm because it will make some of these things really much more obvious than they would have been in the CML latch. In particular, one of the sort of effects that we said was a very important one is the so-called hysteresis, meaning the tendency of the comparator to remember its previous decisions and effectively potentially make different decisions based upon the previous ones. So let's again redraw this strong arm comparator to hopefully really make it clear why there might be this kind of hysteresis here. Okay, so we'll draw our input devices. We have our sort of clock transistor down over here on the bottom. And then we have the sort of cross-couple inverter type of structure. Okay, and then we're going to have, as we said before, our pre-charged devices up over here on the top. Okay, so now let me ask you a particular question. And let's really focus on this, let's call it intermediate or middle voltage here. So, when the clock goes low after you've previously made a decision, and let's again sort of do a plot of this. So let's say we have Vmid plus and Vmid minus. And I plot that versus time. So when the clock goes low, what happens to those Vmid voltages? And I'll just put the clock over here below it just so that it's clear. So let's say the clock went low like this at this time. What happens to those Vmid voltages? By the way, what happens to the outputs when the clock goes low? Yeah, they start charging up. Now, here's the key question. Where were the outputs before the clock went low? Yeah, so one of them would have been at VDD. The other one would have been at ground. Okay? So let's just arbitrarily decide. Let's just pretend that, for example, this side over here, which let me call it VO plus. Oh, I'm sorry, let's actually VO minus. And let's call that VO plus. Let's say that VO minus started at ground and VO plus started at VDD. Okay? And also to be totally clear, let me just relabel this slightly. Let's just call this Vmid over here. Let's call that Vmid minus. And let's call the right-hand side Vmid plus. Okay? So, under that condition, as we just said, when the clock goes low, well, Vout plus basically doesn't do anything. Right? It just stays at VDD because it's already at VDD. Okay, well, VO minus, it's going to start being charged back from ground up to VDD. Now, because of that, you guys tell me what's going to happen on Vmid plus that might be Vmid minus that might be different than Vmid plus. And again, look carefully at the circuit and hopefully it'll be clear what's happening.
Well, it starts going up.
Okay, you said it starts going up. Which one starts going up? Okay, right. So in this case, because this side was VDD already, as soon as the clock goes low and turns off this transistor, Vmid minus is immediately going to start going up. Right? That NMOS transistor over here is just going to start pulling it up. Okay, so let's just sketch that. Right, so immediately as the clock goes low, this starts moving upwards. Okay, now, this is almost, let's say, a 141 kind of question now. So is there anything, let's say, bad about this particular scenario or that, may not be as ideal as we'd like it to be in terms of setting the value of Vmid minus there? Yeah, you're charging up that node through an NMOS transistor. Okay, so that's not to say it won't eventually get to VDD. It's just that as you get closer and closer to the threshold, you have really less and less current flowing to actually charge the thing up. Okay? So indeed, there'll be this initial sort of strong pull-up, and then there'll be this kind of long tail sort of thing. Now, you guys tell me, what's going to happen on Vmid plus? That's unfortunately a little bit different. Yeah, exactly. So unfortunately on Vmid plus, first, this side has to be actually charged up. right? And until that's charged up, the NMOS is completely turned off. So in other words, if I looked at that versus time, there's going to be this kind of delay, and only then are you going to eventually start pulling the thing back up. All right, so now, you guys tell me, how can this cause hysteresis? In other words, how can it cause it so that the comparator actually remembers what the previous decision was and may have a different, let's say, switching threshold or switching behavior based upon that previous decision?
So if V output is initially at V when you switch to recharging, it seems like you're going to be potentially bringing a lot of static power because if V mid plus at the same time, if that was starting at ground, it seems like you have a big voltage drop across that NMOS initially.
Yeah, so the question is that static power or is that actually dynamic power because all you're doing is charging the capacitors that are here? Because notice, there's no path to ground. There's no DC path to ground. You're right that initially, when, let's say, the gate of this is at VDD and this is at ground, there's going to have to be current flowing through it to actually move the other side. But it's not that there's going to be DC current because once you charge this capacitor up to close to VDD, the transistor basically turns off, and there's, again, no path to actually flow current to ground.
Okay.
Is that clear?
I guess I'm wondering why when the clock is high, V mid plus is at ground. It seems to me like it would be higher, I guess.
Oh, okay. So, well, actually, even when the clock is high, so the question was, why is it when the clock is high that this is really at ground? Well, if this output over here is really at ground, then where does this have to be?
Oh, right. Okay.
Sure, but
About the other side.
Oh, you're saying, is this really at ground, or is it? Oh, I see. Okay. This may not necessarily be at ground, although actually, to be totally correct, again, if this is really at VDD, right, and this is at ground, then this transistor is basically totally turned off, right? The gate of this transistor is at ground. So if this, you're right that this doesn't necessarily have to be precisely at ground, but it's going to be really close. Because if it was actually above ground, you'd have a negative VGS on that transistor, right? And any substantially negative VGS would probably make the leakage current of this way, way smaller compared to the leakage of everything else up over there, right? So in other words, you're right, it's not technically exactly at ground, but it's going to be pretty darn close, okay? And by the way, you can almost think of this whole thing as just like a digital circuit, right? Because once it's regenerated, then basically you really just have digital signals everywhere, right? You have a transistor that's on, you have a transistor that's on, you have, a transistor that's on, transistor that's basically off, then you have a PMOS transistor that's on, the output is basically going to be at VDD, okay?
VI plus and VI minus are not really digital.
But are these transistors on or off? And again, just think of it purely from a 141 standpoint now, meaning as a digital guy, is this transistor on or off?
Depends on your common mode.
Okay, you're correct. It does depend on the common mode. If you want this thing to actually operate at, let's say, 4 gigasamples per second, where do you think you're going to put it?
High.
Yeah, so it's going to be on. Now, by the way, even if it was reasonably low, it turns out that because this transistor is essentially quote-unquote off, there's kind of it doesn't really matter how hard you turn this thing on in the sense of this node here is going to have to be close to ground.
No, but it might matter for the left branch.
For the left, well, no, even there, as long as these PMOS transistors are off, meaning their leakage is really small in comparison to whatever current you had through here, then it should still be essentially a ground. Now, you're right, if I put a really, really small voltage here, then, and I get into the region where I'm competing, leakage against leakage, then you're right, it may not really work that way. But most likely it's going to be so slow that that's not really a practical case of interest. It's a good point, though. Other questions on this, or? Yes?
So could you just say again why the V mid plus side has to wait for the V mid minus side to start?
It's not that it's waiting for V mid minus, it's waiting for V out minus to get high. Yeah. Okay, so now to go back to my original question to you guys, why is it that these waveforms would cause hysteresis? And let me maybe give you a hint. Let's say that the clock goes back high at this time right there.
So if you look at your amplified stage in the graph page, then you can see we're already like halfway there.
Right, exactly. So the trick here is, the problem is that when I make this clock go back high, that's when I'm quote unquote doing this amplification stage, right? That's when I'm actually looking at the input, and based upon which of those two, let's say, outputs gets closer to the switching threshold first, that's the one that sort of wins in terms of regenerating in that direction. Well, notice if my middle voltages don't start at exactly the same point, one of them is pre-biased already. One of them already is going to start moving or look as if it was lower before anything even happened with the input. So in other words, even if I put a perfectly zero differential input right at this time, because, for example, in this case, I believe it's Vmid minus started out lower, it would tend to also end up being the one that ends up being low after the evaluation. And you can imagine if I sort of changed exactly where I placed this clock edge, that would change how big this hysteresis effect was. Right? Because if I, for example, waited much, much longer, eventually these things might settle to be very, very close to each other, and that hysteresis effect would go away. If, on the other hand, I pull this clock edge in closer, which, by the way, means you're trying to run the thing faster, then, of course, hysteresis will be larger. Okay, because you've had less time to actually settle the differences between those two things out. So, if you really want to get rid of this effect, if you really don't want hysteresis, and you don't want to have to wait for a really, really long time, what are you going to have to do? How are you going to have to modify the comparator that I've shown here? Yeah, exactly. You can include precharges to Vmid plus and Vmid minus. Okay? So let's just draw that in a different color. This is an example. You could just add another precharged device like this, and another one over there. And indeed, that would basically get rid of this effect. Because now, as soon as the clock goes low, you'll immediately try and drive both of those up to VDD. Now, that's not to say that things are perfect, because of course it still takes time to charge the two sides up to VDD. And indeed, it won't be exactly the same time just because of the effect that we mentioned earlier. But this will be a lot better, because now you've got a good, let's say, strong PMOS driving both of those sides up towards VDD. Turns out there's one more trick you actually may want to play. In fact, actually two more tricks you may want to play. So can anybody else think of some additional things you might want to do if you're really, really paranoid? There we go. The other thing you indeed might want to do is actually add a transistor like this. Okay? So the idea of that transistor is to say, well, you know what? I just really want to make sure that I have absolutely no difference between those two. So I'm actually going to just try and literally short the two of them together. All right, and indeed, this is oftentimes something you'll want to do, simply because, if nothing else, as I said before, with these two transistors, what you're really doing is you're trying to pull the common mode of both of them up to VDD. Okay? Well, let's say that that's not perfect. Let's say you don't exactly get the common mode as high as you'd like it to be. Well, if you add this bridge transistor in, if you kind of think about it, for the same size transistor, I can actually get a much better, or I can get, let's say, much lower resistance in terms of forcing those two sides to be equal to each other than I can by essentially having to, for example, go through one transistor to VDD and then through the other transistor coming from VDD back to the other side. In other words, for the same size device, I'm basically getting twice as small of a parasitic resistance in series there, which is, again, going to force the thing to try and track, or rather force the two sides to really be equal to each other more effectively than just having these two precharged devices. Now, by the way, having said this, is there anywhere else you think you might want to add a bridge transistor like this to the circuit?
Well, yeah, if you're really paranoid, you can also do it in the possible inverter.
Yeah, exactly, right? So, hey, I could have the exact same problem at the output of the inverter itself. Okay, so if I'm really paranoid, and by the way, my recommendation in general with circuit design is you should always be really paranoid, you'll add the bridge transistor there too, for the exact same reasons we just mentioned. Now, it turns out there's even one more thing you're probably going to want to do to actually totally get rid of hysteresis here. So does anyone see where else you might actually have some funky hysteresis coming from? Yeah, exactly. It's the drain of the clock transistor. So by the way, for those who couldn't see it, there's only really one more node left that we haven't touched in one way or another. right? And that's exactly the drain of the clock transistor. So now you guys tell me, why is it that you might pick up some hysteresis from this node right here? What weird thing could happen there?
It could be higher than one of the inputs.
Okay, I guess in principle it could have been higher than one of the inputs. So that's generally, I mean, that is possible, although that's usually not going to happen. But more, let's say importantly, what else could happen?
Well, I guess it's pretty likely actually, because if you start, well, no, maybe not because of the clock down there. Say if your clock down there was kind of delayed somehow, then like one of them could be charging up, while the other one is doing nothing.
Okay, so you said that one of them might be charging up the node while the other one is doing nothing. That's certainly true, but what is it that would, let's say, cause hysteresis? In other words, what would have to be true about this voltage here in order for you to actually see a hysteresis effect? And to be totally clear, hysteresis again means that the threshold of the comparator is different depending upon the history of previous data you fed into it. So what's the only way that you could get hysteresis from this node? Is it mismatch? Because by the way, I've shorted those two. The sources of those two transistors are shorted to each other. I'm not going to change that. I'm not introducing resistance. If the transistors themselves are mismatched, there are some second order ways that could cause hysteresis, but I claim I can get hysteresis due to this drain node, even without any mismatch whatsoever. So I've got a common mode node, but somehow I need to get hysteresis out of this. And trust me, you can get hysteresis out of a common mode node.
Could it deal with resistance across the node?
I'm not even going to put in resistance for a second. Yeah?
Is the clock bias somehow like the clock threshold bias is not changing over time?
Okay. So that's an interesting one. You said, is the clock threshold changing over time? It could indeed be changing, but I want to really identify what's, let's say, the fundamental root cause that would make the clock threshold change. What is it about this particular node that would have to be true in order for me to somehow get some memory of what the previous data was?
It's not an infinite impedance.
Okay, it's not an infinite impedance. What does that mean?
It's not a perfect current source. That node can be moving on.
Okay, so you said it's not a perfect current source. The node can be moving up and down. The node indeed can be moving up and down. So now to be very specific, if I have hysteresis, what does it mean about this particular node, especially if I looked at it right before my clock went high? What would cause hysteresis? Okay, the parasitic capacitance is involved in the picture, but I think maybe you guys are overthinking it a little bit, so maybe I'll just give you the simple answer. So at the end of the day, all that has to be true for you to get hysteresis is that the value of this node here is not always the same. Right? If in one evaluation it happened to be, let's just make up a number, 500 millivolts, and another one it happened to be 550 millivolts, guess what? The whole circuit will behave differently. If the whole circuit behaves differently, that indeed can very easily translate into a different input threshold. Right? So as an example, now we can start introducing some of the effects you guys mentioned. Right? As an example, maybe the exact threshold of that clock transistor is not the same. Maybe there's some mismatch in these transistors, and so if the source node is different, that gives you a different input differential, and so on and so forth.
But if that drain node is like different, that would only cause hysteresis if there was mismatch in the input resistors.
Not necessarily. Right? Because notice as an example, let's say that from whatever reason there was a slightly, you said it was only due to mismatch of the input transistors. You're absolutely right. Mismatch of the input transistors is the dominant effect. However, it doesn't have to be. So as an example, let's say there's even mismatch in these PMOS devices up over here. Guess what? If this source node is starting at a different point, that will change how much of this mismatch actually shows up at the input. Because the quote-unquote effective gain you get in this initial phase would be different. Okay? I believe I can actually even come up with situations where even if sort of common mode-wise something, that there was no real mismatch, there was just some common mode thing, I believe I can even come up with scenarios where even that would change the mismatch. You're right, however, the zero order thing is indeed that if there is any mismatch in here somewhere, then variation in a common mode can easily translate into a differential error. Yeah?
Yeah, I guess I was going to say is if the common mode was messed up enough where that it didn't have enough time to latch.
Yeah, as an example, right? So you said that, let's say as an example that this voltage was just, stuck at some really weird place. For example, was stuck at VDD and there was so much parasitic cap there that you just never got the input devices to really turn on. Yeah, that would be another great way to sort of make the thing fail. That's a pretty catastrophic failure, so that usually doesn't happen. But indeed, that's another possible mechanism for something like this. All right, so now, by the way, you guys tell me, how do I fix this? What was my solution everywhere else? Yeah, I precharge it, right? Okay, so let's just do the same thing. So let's just add in another PMOS transistor here, also tied to the clock, and just force the darn thing, for example, to VDD every single cycle. By the way, this is just a really funny way of drawing an inverter, but if you look at this carefully, this composite blue and red thing here is really just an inverter driving the tail node. And again, the only reason you do that is just to make sure that that tail node has a very, very well-defined voltage every single time right before you make that decision. And again, because if it doesn't, well, another way you can potentially pick up some hysteresis. Okay? Now, I will mention, this is really the sort of utmost, most paranoid way to build this thing to get rid of hysteresis. There are some penalties you pay for it. Obviously, there's a lot of clock transistors. There's a lot of extra parasitic capacitance you're introducing. But nonetheless, if you really don't want to have to worry about this hysteresis problem, this is by far, let's say, I would strongly recommend you follow this kind of structure, simply because it allows you to not have to worry about it. Or at least to zero order, it allows you to not have to worry about it. Make sense to everybody? Or? Okay. So now that we talked about hysteresis, it's also useful to basically just briefly review how you might actually construct a test that would, in simulation, let you characterize the hysteresis of your device, or of your comparator. Turns out the most popular way of doing this is with what's called an overdrive recovery test. And the idea is quite simple. So what you'll typically do in this kind of simulation is you'll take your inputs, you'll start them out at essentially the largest magnitude in one direction as you possibly can. So as an example, I'll make them as positive as they can possibly be. And then what I'll do is I'll clock the comparator a bunch of times to make sure it's really seeing this very big positive input. And then what I'll do is I'll basically transition these two inputs to flip their sign, but to do it with some relatively small delta V. Okay, so in other words, the amplitude now I'm going to make it go from all the way from the largest, for example, positive thing it could have been, to the smallest absolute value in a negative, or to a very small absolute value in the negative side. So the idea here is very simple. If you then sort of sweep that delta V, what you can do is you can actually watch whether, and by the way, of course, you have to clock the comparator one more time here. What you'll then do is watch essentially how big of a delta V you need to actually make the comparator resolve the right way. So let me just draw sort of another, let's say, waveform to make sure that that's clear. So let's say I had an ideal comparator. So in other words, I'm going to look at the output voltage of that comparator, and I'll just do one side of it just for the sake of compactness, versus time. And it's, the time axis here is the same time axis as this overdrive recovery input that I've drawn above it. So if I've got an ideal comparator, then what should happen is, as soon as I clock it after that delta V, change at the input, it should flip its output to go, in this case, to 0, right? Because I made the input negative. Well, if I actually have some hysteresis, and that delta V is not big enough to overcome that hysteresis, then what you'd see is instead something that, for example, would look like this. So right when it was supposed to make a decision, it would maybe glitch, but then it would come back and stay at the previous output. Okay? So what you see is that as you increase that delta V, in some senses this glitch would get bigger, but may still come back. And then eventually, if you make it really big enough, it'll actually resolve to the proper output. Now, to be totally, let's say, fair, or to be totally accurate, I should say, if you guys remember when you talked about maybe metastability in one of your digital classes, this is exactly the same effect in that if you make that delta V, just barely the same size as the hysteresis, what may even happen is the thing just sort of hangs out at some point for a while, and eventually maybe it does indeed resolve the right way, but it could even actually go back the other direction as well. So the whole sort of, let's say, point or trick of this test is what you'll basically do is you'll sweep that delta V until you see that indeed your output resolves in the correct direction. Now, to be, again, let's say complete, it's not just that you'll look for it resolving. It's actually, remember, you want to run this comparator at a certain speed. So in fact, what you'll really do is you'll look at, if, for example, I wanted to make sure that my comparator decided within this amount of time, I would actually look at, okay, well, did the thing resolve, let's say, to ground, or to something close to ground, by this point in time, which presumably would be the time at which you want to use the output of that comparator. And as you can imagine, the closer that is to the time at which you actually triggered the comparator, the larger delta V you'll need to apply to actually essentially overcome whatever hysteresis there was inside of the device. Does this make sense to everybody? Or? Okay, now I've focused on this as mostly sort of being a test for hysteresis. But it turns out you can actually use this same test to really give a lot of other interesting information as well. So as an example, if you had an offset in the comparator, and you set this whole thing up so that you were really trying to fight, in the direction that was bad for offset, this delta V that you would find would tell you not just how much hysteresis you had, but also how big the input referred offset of the device was. So in fact, when you get to sort of your third phase of the project, you actually have to build your own comparator. The way you should characterize the so-called offset that we've been using in all of the Burr equations, which in reality should actually include offset plus hysteresis, is indeed by using this overdrive type of recovery test. Because what you'll see, you'll put in all the different offsets in the transistors in the circuit, and then essentially you'll do this overdrive recovery test to really see how much both offset is there and hysteresis in order to make sure the comparator really resolves the right way. Make sense to everybody? Or?
Is the delta V different for the two sides when you have offset?
Yes, absolutely. So the question was, is the delta V different for the two sides when you have offset? Absolutely. And in fact, even the hysteresis may be quote-unquote different on the two sides, simply because if there are offsets and mismatches, there's no particular reason why the whole structure has to be symmetric. And so, of course, when you do this, you should always test it in the direction that you know is bad. And I guess if you don't know, although really you should, you'd obviously have to try both directions. Yes?
So how do you distinguish the offset from the hysteresis?
You don't know what's what here. Right? You don't know what's offset, you don't know what's hysteresis. And this, if I just did this one particular test here. Okay, now, in reality, what you could always do is essentially try and do a plot of, and I'm going to simplify this somewhat, but you could try and do a plot of, for example, what the comparator does from its, let's say, V out versus V in curve, if you sweep in one direction versus the other. And then depending upon how you'd like to define it, you could, let's say, think of this middle point as being the offset, and then the delta around those two middle points as being the hysteresis. But really, it's kind of a definitional thing. It doesn't really matter. It tells you, at the end of the day, how big does your signal have to be to actually make it consistently flip one way versus the other. That's really what you care about. Make sense? Or? So one other thing I will mention here is that this particular test, specifically for something like a strong arm, may not make a big difference in terms of you really slamming it hard to one side or the other initially and then giving a small input. But if you really start building some of these more, let's say, analog types of comparators, in particular, as we'll see in a second, you're going to tend to want preamps in front of these comparators. This is really the test you want to do because it really stresses what would happen essentially in the whole analog signal chain in front of the comparator in terms of trying to force it to basically get, let's say, back as far as it needs to go to actually flip the comparator output. And in particular, this becomes a big issue when you build comparators or, let's say, amplifiers that have relatively high impedance outputs. So as an example, let's say that that's the first stage of your amplifier in front of your comparator. Then if you put a really, really big differential input into this thing, well, the output over there can almost hit full rail, right? It can actually get basically twisted in a very, very big way. So if something like that happens, then when you then apply this very small input, you basically have to charge or discharge those nodes through a very, very large voltage swing before it would finally cross back over to get onto the right side, to the right, have the right sign in the differential output, right? So as an example, if let's say the node started like this, I have to do something like that before and of course it's only here when I finally will get to cross over, okay? So it turns out that oftentimes, exactly to avoid this kind of problem, for the preamps that people use in these comparators, they actually won't let it have too big of a swing. Because if the swing really is, let's say, something like VDD, and you end up just slewing, meaning you're limited by what those bias currents are, it could take quite a bit of time before you really slew all that current all the way back and get the line to flip again. So as an example, what people will very often do is use these so-called clamps. And I'm just drawing a picture of it right now. Where the idea is simply to make sure that if the swing ever is going to approach something that's too big, that you know will take you too long to actually regenerate from, you just clip it. Okay, so this sort of, let's say, these two things are just almost diode-connected transistors just tied, let's say, back to back. Again, the whole idea here is just that if, for example, this side gets too high compared to that side, transistor turns on and clamps it. If this side gets too high compared to that side, again, the other transistor turns on and clamps it. You can almost think of it like a diode. Yes?
Won't that cause problems when you do something more than 2 PAM?
Okay, so you said, won't this cause problems if you did something more than 2 PAM? Well, it all depends, right? Because obviously this is indeed a nonlinear mechanism, but depends on when you cause it to kick in. So if you cause it to kick in at a, let's say, swing that's large compared to the full range you might have on the signal coming in, then it's fine. Now, by the way, there's another, let's say, interesting thing to mention here, which is, if this is really a part of my comparator, then you guys maybe tell me, if I put some nonlinear element that might clip in front of a comparator, as long as its threshold is in the right place, do you care that that element is nonlinear or no? I heard somebody say it. Just speak up. No, right? Because, by the way, when you have a comparator, you're pretty much doing the most nonlinear thing you can possibly do to it anyways. Okay, so if I put another nonlinear thing in front, well, not usually a big deal. The trick, of course, is that you have to be very careful to make sure that the threshold is where you want it to be. Because if it's not, that would sort of may cause it so that the comparator threshold can't be placed where you want it to be either. Good questions. Yes?
So these, like, it seems like the clamps are, in some ways, almost like a cascade or something like that. I guess I'm not too much on how the clamp works.
Oh, okay. So the question was just how exactly does this clamp work? And let me just draw it a slightly different way. So let's say this was, and I'm just drawing a little bit larger to maybe make it easier to see. So let's say that's your differential amplifier. So if I, for example, just put a diode here like this, right? The idea here would be that if this was some ideal diode with some certain threshold, then as soon as the voltage got above a certain level, the diode would turn on and basically force the differential output to be stuck at that voltage. Okay? Same exact idea with this clamp circuit here. So I just took this NMOS transistor and tied it into a so-called diode-connected configuration to exactly cause that kind of effect. Now, by the way, I should mention, practically, especially in modern technologies, these clamps may not be great because you need at least a threshold across it, and the threshold could be a pretty large fraction of the power supply. So I'm not claiming this is exactly how you'll build it, but it's important to sort of know about this concept just because, again, it is very often useful to make sure that you don't have too much swing in those stages in front of the comparator. Because if you do, you can really end up with long, essentially, delays or, let's say, large hysteresis effects if you really do this overdrive kind of recovery test. Make sense to everybody? Or? All right. Now, lest you thought that this was the end of the story and that, now you're done and you know everything there is to know about comparators, there's one more pretty important effect that we have to worry about. And that's this so-called kickback. So we talked a bit about this last time, but just to sort of make sure it's really clear why this can be a big problem, let's just do the following thought experiment. So let's say we've got a comparator, and we did it, for example, with one of these strong arm kind of things. So if I looked at my output voltage, its swing was basically from 0 to 1 volt. Okay? If I then also look at the input voltage, let's say that as we had started out with on everything here, I wanted to be able to resolve, for example, a 1 millivolt peak-to-peak swing, or a maximum or a minimum, let's say, a differential voltage at that comparator. So what would be one really bad thing that might exist inside of this comparator that could actually very easily make it so that you can't even see that 1 millivolt input signal? Okay, offset is certainly true. That's definitely there. We're going to talk a lot more about how we get rid of that. There's another thing. Okay, noise, that's also correct. But I'm saying, let's say, something more deterministic in nature. Okay, clock feed through could do it. That's actually an interesting one. And by the way, how would you get clock feed through? Let's say, elements do I have to add to this particular picture to make it so that there might indeed be some clock feed through? Yeah, capacitor. And in this case, as an example, what would be like, if I was specifically worried about the clock, what would be probably the worst capacitor to add? Like, where would I add that capacitor to make the clock feed through really bad? Yeah, exactly. Input to clock. Right? Because actually, you guys bring up a good point. This clock could also easily have a 1 volt swing. So if I just have a capacitor from the input to the clock, well, guess what? That could very easily cause a glitch or some other error, which is way larger than 1 millivolt. Because I need, for example, 1,000 to 1 attenuation just to get from 1 volt down to a millivolt. By the way, where else might adding a capacitor be bad? Yeah, input to output, right? Because for the same reason, I've got a volt of swing at the output, and unless I'm really, really good, I need something like 1,000 to 1 attenuation to make that 1 volt swing at the output not screw up my 1 millivolt input. All right, so now you guys tell me, and I'll just sort of draw, let's say, part of the strong arm comparator. And let's say this is Vn plus, and that's Vn minus over here. Okay, where might you pick up some of these types of capacitors that I'm indicating here in the strong arm comparator? And this is, of course, the clock. Where might those capacitors be coming from? Whether you like them or not. Yeah, exactly. There's always going to be a CGS here. And as we said a second ago, I might actually want a PMOS transistor here for hysteresis purposes. Okay? And there's also, of course, going to be a CGD. And as we again also said before, I probably want some PMOS transistors here to precharge that output as well. Or that intermediate node, I should say, as well. Okay, so notice, I've got plenty of ways that I've basically got my very, very sensitive inputs capacitively coupled back to nodes that swing with the full power supply rail. So now, in this particular instance, what would be the dominant effect from basically this capacitive coupling? Like, what direction would it move the inputs? Right when you make the evaluation. So right when the clock goes from 0 to 1. Yeah, it's going to go down. Right? This node, this node, this node, they all start at VDD. And when the clock goes high, they all start moving down. So all of them are basically going to push some, let's call it negative charge, into those outputs. Now, into those inputs, you're right. All right, so how bad is that? Well, if everything was perfectly matched, then you could actually argue that this should be a totally common mode effect. Right? Because if the input devices are matched, if the precharge devices are matched, if everything here is sort of symmetric, then all that should happen is the input gets pushed down, but it would be a totally common mode glitch. Problem, of course, is that life is never that good. The input transistors, for example, never match perfectly. The pre-charge devices, for example, never match perfectly. And in fact, as I'll sort of show in more detail in 1 second, turns out even if the comparator itself was perfectly matched, unless my source driving it, right, the thing actually generating those differential signals, unless that was perfectly matched, then even if the comparator itself is perfect, the common mode current kickback would get translated into a differential current, or a differential voltage. Simply because, again, if these two resistors are not the same, then guess what? You're going to end up with a differential input voltage due to that common mode current kickback. Make sense to everybody? Or? All right, now, you might think that this is maybe not that big of a deal, but turns out there's lots of very subtle ways that this can become a very important effect. So here we've mostly talked about one comparator sort of kicking back onto itself. Turns out there's a lot of situations where it's even more complicated than that. So to give you an example of why that might be the case, let me just sort of ask you guys a little bit of a question. So right now you guys are working on your project on a 4 gigabit per second link. Anybody have an idea of what might be an easy way to make that, for example, operate at 8 gigabits per second without making too much modification to the sort of, let's say specifically to the comparators themselves, but more generally to sort of your front-end hardware? Okay, yeah, you use twice as many comparators, and in particular, how might you clock those comparators? You could use 2 what? Oh, 2 signal. Okay, I see. Okay, so you said that I could basically just, take 2, let's say, parallel channels and run them both at 4 gig. That's correct. I want 8 gig on the same channel as I had before. And let's not worry about equalization and signal, all the signal integrity and stuff like that. I want to take something very similar to the hardware I originally had and just run it twice as fast. And I'm even lazy. I don't even want to redesign my comparator at all. Okay, you said go to 8 PAM. That is indeed one way of doing it. Although I would have to, let's say, so if I went from 4 PAM to say 8 PAM, I'd have to go from 3 comparators to 7. Okay, so I could do that. Let's just stick with 2 PAM for now. What's another way of just making the thing run faster? Faster clock. Okay, I could do a faster clock, but if I do a faster clock, I probably have to redesign the comparator and make sure it runs that fast, right? What's something else I could do? Yeah, exactly. I could just have 2 and trigger them off of opposite phases of the clock. Okay, so as an example, I could take my original comparator that, for example, was triggered by clock, then just take another one and trigger it, for example, by clock bar. Right? Of course, this would be my analog input. So indeed, if I did something like this, and by the way, this is extremely common. This is often, let's say in the ADC world, this is what people refer to as time interleaving. In the high-speed link world, or let's say in the memory world, this is sometimes referred to as double data rate, or DDR. So all the DDR memory, or DDR DRAMs that you bought, this is exactly what they're referring to. They just mean that you make a decision on both edges of the clock. All right, so that looks nice. Well, why did I bring this up in this kickback context? Well, notice before in this previous picture here, it was mostly your comparator kicking back onto itself. Right? And so you could have argued that, well, hey, as long as everything was nicely matched inside of this comparator, then the kickback would have mostly been common mode. Well, in this scenario here, notice that whenever, let's say, that upper comparator makes a decision, at the exact same time, that lower comparator is being precharged. And remember, when you precharge, that means you have to take whatever the previous decision was and erase it. That means that the kickback you're going to do fundamentally has to depend upon the output voltage. Because again, if we just, let's say, for example, look at this picture here, when I look at the case where the clock is actually going from high to low, well, we said that, and actually I guess we should look all the way back over here. Right? As we said, initially, one side was going to be at ground, one side was going to be at VDD. So the side that's at VDD doesn't move. the side that was at ground, has to move up to VDD. That means that if I looked at, if there was any capacitive coupling from here back to the input in one way, shape, or form, guess what? I'm going to have a differential kickback. Does this make sense to everybody, or? So again, just to be totally clear, what I'm basically saying is that right when this upper guy, for example, is deciding, that's exactly when I may have to say that this guy would have to go, for example, from a 0 back to a 1. In other words, that's exactly when I'm pre-charging it. Okay, and so that means that if it was a 0 before versus if it was a 1 and it's going to go back to a 1, in that case, that's a different kickback. Right? There's a different amount of charge that's going to go flow back onto the input like that. So that means that, indeed, you really have to worry about this kickback as causing a differential error for that upper comparator there that's making its decision. All right, so now you guys tell me, what do you think is going to be the most effective way to, again, make it so that you just build your circuit so that you're really, really paranoid and you have to worry a lot less about these kind of kickback effects? Okay, you said 2 amplifiers. What kind of amplifiers? Okay, yeah, so that's exactly right. So it turns out that exactly because of these kickback types of effects, whenever you build a comparator, you're almost always going to want to put a so-called preamp in front of it. Okay, so in other words, you're almost never just going to have that, let's say, latch or regenerative kind of structure. You're almost always going to put another amplifier in front of it. Where the whole idea of this amplifier is really going to be twofold. One is if I have that amplifier, as long as it's, let's say, a good amplifier and has good reverse isolation, then even if I get some kickback onto this node here, that would at least stop a situation like this, where you'd have one comparator kicking back onto the other with a very large capacitance, right? In other words, the amplifier would sort of isolate those two things from each other. The second and perhaps more important point is that there's a very specific way you're going to want to build that amplifier to make sure that even the comparator kicking back onto itself has as small of an effect as possible. So if we go back to this picture here, what do you think you're going to want to make the source impedance look like in order to make the kickback as small as you can possibly make it? Yeah, you're going to want a very low impedance, right? What else is really important about this impedance if you want to make sure that your differential kickback that your common mode kickback doesn't end up causing a differential error? What else is really important about these impedances here? Yeah, they have to be exactly matched, or as matched as close as you can possibly make them. So, given the two things we just said, how do you guys think we're actually going to want to build that preamp there? What do you think is a good structure for that? Okay, so you said a source follower. And that's actually not a bad guess, but we're going to see in 1 second why that may not be the best way of doing it. So let's indeed draw this as a source follower. Okay, so in terms of low impedance, that's a pretty good low impedance driver. That I totally agree with. What's the problem? Okay, so there's a big input to output coupling. Let's not even worry. I mean, you're right, although that's maybe not so, it may not be horrible, although that is true. There's another issue which is related to the second thing that we talked about, making these, what did we say we had to make these besides just being low? Matched. Why do I claim that this might not be the best way to do that? Okay, so you said that the output impedance of those structures is basically 1 over GM. And 1 over GM is very sensitive to size and bias point and things like that. There's a lot of truth to that, but I would claim even if I got all of those right, there's still a fundamental problem. Okay, so you said that the RO of these things depends upon the input. And that's actually exactly the issue. Now, when I say RO, I don't mean literally the output impedance of these transistors, although that is also correct. It's actually that even the 1 over GM would vary, right? Because as you move the inputs around, it's not that the GM is really constant, right? It actually varies with the input. And so even if I put a relatively small differential input in, that means that the GM of the two devices would be slightly different, and therefore the output resistance of the structure would also be slightly asymmetric, meaning the P side would not be necessarily the same as the N side. Okay, so that's actually why you may not really want the source follower kind of structure. So now having said that, what kind of structure do you think you might want? What do you think would be a good way of making that output impedance very, very symmetric?
Just using OTA or resistive.
Okay, you said just use an OTA with a resistive load. By the way, some people wouldn't call resistive load OTA anymore, but yes. So in other words, turns out the most common and probably most effective preamp is really just a resistively loaded differential pair. And again, the reason this is really so effective is, of course, one, you can make the impedance low just by using relatively low resistance values, which is another way of saying that typically the gain of these structures won't be very high. But second, and more importantly, the advantage of doing something like this is that as long as these resistors are reasonably linear, and to zero order resistors typically are pretty darn linear, then even if there was some differential input over here, the output impedance of this structure stays relatively constant across that entire input differential voltage range. Okay? So in other words, as long as you make these resistors small compared to the RO of the transistors, you'll really, largely speaking, get rid of that differential output impedance imbalance. So you said you're burning a lot of power. Well, so you guys tell me, how much power are you burning for this amplifier here? Okay, yes, you said I bias. That's correct. It's I bias times VDD. What is that I bias? What's that magic equation we've invoked like, 30 times or so in the course of this class? Okay, sorry, say that again? Okay, you said 2GM over V star. I want the equation that it's like the digital CV squared F equation. Okay, so I think collectively it was given, but I'll just write it out. So it's really just I bias is equal to the gain times the bandwidth in radians per second times the load capacitance times V star. All right. So the argument was, well, won't you end up burning a lot of power on this preamp? Well, I would say you're burning as much power as you were burning to drive that load cap. Okay? So you're right that if I worried about the absolute lowest power system I could ever possibly build, and I don't care at all about performance, indeed, there's some overhead from this. But if I cared about the performance, and in particular if I really cared about this kickback, which, by the way, just try it once, build a comparator and drive it with a, let's say, somewhat crappy preamp, you'll see that kickback can be huge. Because notice, again, if I've got a volt of swing out over here, I need quite a few dB of rejection to knock things down to that millivolt kind of range. Okay? So you're absolutely right. You're going to pay some power here. But it turns out that in practice, this is typically a still very, very cheap way of doing things, simply because as long as the load cap you're driving is not too big, the power you're going to spend on this is not going to be that big either. In other words, the power of this stage is just proportional to the load cap you were driving anyways, which would have been true for any other stage driving the comparator as well. The only penalty might be if you end up with an additional stage that you didn't want. Okay? But if you needed multiple stages anyways, well, no real big penalty for doing this. Other than perhaps just that, as I said before, this gain will tend to have to be small, simply because the way you make sure that this resistance is small compared to the RO is you make sure that the gain you're shooting for is small compared to the intrinsic gain of the device. Right? And especially today where your intrinsic gain of the devices is 4 or 5, that means you really can't target a gain of more than about 1 or 2. Make sense to everybody? Or?
Why do you actually want to gain at that stage?
Oh, it's not that you necessarily have to have gain. The question was, why do you want gain? It's not that you necessarily have to have gain here. It's just that obviously if you do have some gain here, then for the same 1 millivolt sort of signal I deal with there, now if it's 2 or 3 or 4, obviously it's that much easier for the comparator. That's all. Other questions on this? Or? Yes?
I have a question about comparators, and in the project they're all
Okay, great question. So the question was, in the project that I gave you guys this semester, you actually needed sort of variable threshold comparators, because you needed some that were not sitting at 0, but were sitting at some other reference point to be able to decide on the 4 PAM levels. So you asked in practice, is everything that I've showed you so far basically a 0 threshold comparator? And the short answer is yes. Everything that I've shown you, at least without some additional modifications, ideally speaking, would have been a 0 threshold comparator. So as we'll talk about probably in about another lecture or so, you're going to have to add some extra hardware to actually intentionally change the threshold of the comparator. Now, the good news is, well, maybe the combined, let's say, good and bad news is, it turns out you're probably going to have to add something that looks like that anyways, because even though this is ideally 0 threshold, as we're about to get into in 1 second, and in fact, this is, let's say, the perfect segue into the next set of lecture notes. Oh, wow, that's interesting. As we're about to get into in this next set of lecture notes, unfortunately, whether you like it or not, your input devices are not going to match perfectly. And as we'll see in 1 second, you can very easily get sort of mismatches on the order of 100-ish millivolts between your input devices. And as hopefully is very clear, that's big enough that if you didn't do something about it, it would probably really substantially affect the performance of your project. Okay, so we'll come back to that one in 1 second, but maybe just to make that totally clear, let's just sort of take actually, you guys didn't finish phase 2 yet, so I'll ask this question later. But we'll see once people finish phase 2 how big of a swing they were typically using. And what you'll see is that oftentimes that swing is like 10, 20, 30 millivolts, which, as we'll see, is going to be way smaller than the offsets we're going to be seeing in our devices. Okay, so the somewhat long answer to your question was that indeed we're going to have to add some hardware to make the thresholds of our comparators be variable. But it turns out we're going to want to do that anyways, just to make sure that even when we intended it to be 0, it'll still actually be 0. So hopefully that sort of answered your question. We're going to come back and talk a lot more about that in probably about a lecture or so. All right. So as we said, we're really going to care a lot about the sort of matching between the transistors. We've mentioned it, many, many times already in the context of common mode rejection, power supply, and etc. But in the specific context of the project, it's really going to be that matching between the transistors, which is largely speaking going to set the offsets of your comparators, which, as you've already seen, is very directly related to the power, performance, and etc. of your Link projects. So the question really is, of course, going to be, how well matched can you actually make these devices? And so what we'll be seeing through basically the rest of this lecture and into next time is that that's not just going to be some arbitrary answer, but it's actually going to be directly set by your design decisions. In other words, there are direct things you can do from a sizing and, let's say, circuit design standpoint that will actually control how much offset you would really be seeing or how much mismatch you'd really be seeing. Okay? So before we, let's say, dive into the details of that, I do need to spend a little bit of time just categorizing what I mean when I talk about device mismatch, or really what kind of variation sources there might be. And as you can kind of hopefully tell by the headings here already, they're largely sort of broken up based upon kind of the spatial extent of those variations. So as an example, if you go and you ask, let's say, the fab guys, well, how much variation do you have in your devices? They'll typically give you the composite of a whole bunch of different effects. So as one example, they may say, well, okay, I have a die-to-die variation of some number. And what they mean by this is that if I looked at all of the devices or all of the transistors on one particular chip, and I compared them against another chip, then roughly speaking, all of the devices on one chip versus the other, within the same chip, they would look the same as each other. But from one chip to the other chip, they may look very different. Okay? That's kind of, let's say, a long-range spatial variation. Similarly, even within a single particular chip, if I looked at, for example, one transistor that was sitting over in this corner of the die versus another transistor sitting over in that corner of the die, those two will also have some variations relative to each other. Right? And you can imagine that variation will be larger or in addition to the variation you might get from two transistors sitting right next to each other. Okay, so that's the so-called within die variation. And that's just saying that within a certain region of the chip, maybe all the transistors look the same. But across those regions, you actually see some variations or some mismatch. The final one is the so-called local or short-range variations, which is now literally at the level of every single device. They're all slightly different from each other. Right? Even if I take two transistors, put them right next to each other, they will never be exactly the same. And as I indicated in the slide here, this is usually the most important source of mismatch that we're going to be worrying about. And hopefully it's obvious why this is really the most important one. Right? Because just as an example, let's say I really did want to build a low offset comparator. You guys tell me, would you want to build that by taking one side of the comparator and putting the transistor on one corner of the die and putting the other transistor on the other corner of the die, or no? No, right? That's silly. Why in the world would you do that? Because even if you ignored the mismatch, you'd have some really long wire running between the two, and obviously the parasitics would be way, way larger than if you just put the two darn things right next to each other. Okay? So on the net, this is really what we're going to spend our most time worrying about, and will be the focus of really the rest of this lecture. All right, so if we look at that local variation, which is again just two transistors essentially right next to each other, there's actually lots of different sources of variation. And some of them will be deterministic, meaning that at least in principle you could have predicted what they would have been. And others will be more random, meaning that just like with noise, all we can say is something about the statistics of those variations. So just really as a reminder more than anything else, if we look at those deterministic sources of variations, all that's really saying is that, as an example, if you took one transistor like this, and you compared it, for example, to another two transistors like this, I would argue that no one of those transistors would behave exactly the same. And again, from a purely deterministic standpoint, I would argue that none of them will be the same. So again, just to maybe sort of see how good your guys' memory is, or to see if you can, get a little bit of a jog from what's written on the slide, why might each of those three transistors be different? What are some of the physical effects that cause them to be different? Or physical, let's say, reasons. Okay, you said they're different surroundings. That's absolutely correct. They are in different surroundings. Why is that important? Like, what does that end up causing? Okay, yeah, you said differences in photoresist, and in fact, that is actually a very big one. So, turns out that as an example, if you have one piece of poly sitting by itself versus a piece of poly sitting next to another piece of poly, the rate at which you etch that polysilicon is actually different. Okay, because for example, the density of the photoresist is different. All right, so that means that, for example, if I was to draw this one transistor here, the channel length of this device might actually be very different than the channel length of these two devices. All right, that's just one simple example. Turns out it's even way more complicated than that. So if you look, especially in some of the more modern technologies, people are playing a lot of, let's say, clever tricks to try and improve the performance of the transistors. Just as one example, people are doing these so-called stress tricks, where they either stretch the transistor channel or intentionally compress it to improve the mobility of the electrons or the holes. Well, if you do that, the amount of mechanical stress you apply actually strongly depends upon what other shapes and structures are around you. Because mechanically, obviously, the sort of the forces are different. Okay, so it means that, again, two transistors next to each other, not at all the same as one by itself. All right, so there's going to be a bunch of these deterministic sources. But the good news is that if you really follow all of the rules that we talked about way back in the second or third lecture of the class, largely speaking, you can get rid of them, at least from a mismatch standpoint. So in other words, you can make it so that maybe all of the transistors will behave a little bit differently than you expected from your model, but at least they'll match against each other, right? And again, the whole trick there was really sticking to these unit cell types of layouts to make sure that the local environment every single device sees is exactly identical. So really, the biggest sources we are going to worry about are these random sources. And again, these are the ones that I can't actually tell you exactly what the value of the threshold is, or threshold, or whatever it is going to be. I can only tell you statistics about it. Turns out there's lots and lots of reasons why there's actually going to be truly random sources inside of random sources of variations inside of the transistors. So the most common one that people talk a lot about is the so-called random dopant fluctuations. So if you remember, the way you actually sort of build a P plus or N or any kind of, let's say, type of semiconductor is you typically take a wafer that has some initial type to it, let's say a P type, and then if you wanted to get, for example, the N plus source and drain regions, you pretty much literally bombard it with a bunch of ions. Okay? Unfortunately, there's no magic little dude sitting inside of this ion bombardment thing that's counting the number of atoms going in. All right? Now, lest you think this is me just making a joke, in a modern transistor, if I looked at how many atoms were actually contributing to set the threshold device of that transistor, it's order 20 or 30, maybe 40 or 50. Depends on exactly which technology you're talking about. So that means that the presence or absence of one atom can actually make a difference. It's actually something you could measurably see whether or not it's there. Right? Because, hey, if I've only got 20 in total, one atom is a 5% change. Right? So that means that you indeed should expect to see some pretty big variations just due to whether or not that dopant atom happened to be in this particular transistor or not. All right? Similarly, when I drew this picture over here of these transistors, that was kind of assuming, and by the way, here you have to maybe stretch your imagination a little bit, that my artistry was better and I had perfectly straight lines and all these other things. In reality, of course, when you're doing the photolithography, if a photon happens to hit one particular point or not, or if some number of photons happens to hit one particular point or not, that will actually change exactly what pattern you get. So as an example, if I look at that piece of gate poly, in reality, it always looks something like this. And so even though I said, well, the length of this transistor is blah and the width is blah, well, if I have something that looks like this, what the heck is the length and what the heck is the width? Right? It varies, obviously. And again, whether or not a photon happened to hit that point right there or not would actually change exactly the dimensions, or the quote-unquote effective dimensions of your transistor. So as I said, there's lots of these, let's say, sources of random variation. And so what we're really going to do in sort of the rest of this lecture, which we'll finish up next time, I won't dive into that, is look at what those random variations are and look at a very simple model we can use